In the last video, we were taking a look at fluid statics, and we'll continue to extend our exploration of fluid statics a little bit and take a look at Archimedes' principle. The original story of this has to do with the Greek scientist Archimedes, who was commissioned to figure out whether a crown was made of pure gold or whether the goldsmith had diluted down the crown with some silver and pocketed the rest of the gold for themselves. Whether the goldsmith was fraudulent or not, that detail is lost to the story. However, the story goes that when Archimedes was brainstorming all of this, he realized that he could suss this out if he could figure out the density of the crown. But to do that, he needed to know its volume. And when he was hanging out over at the public baths, which was just kind of a thing you did recreationally back then, sort of like hanging out at a coffee shop today, really. He got into one of them and noticed that the level of the water changed, and he realized that he could deduce the volume of the crown by immersing it in water and measuring the spillage. He then became pretty much the first known streaker on record, running through the streets of Syracuse screaming "Eureka, Eureka," which means "I got it." How much of this story is factual, who knows, but this is the story that's always told. And I thought it was an amusing starting point for us. Anyway, let's go and take a look at how this winds up getting extended to look at things like, say, an object that's floating. Keep in mind that Archimedes' crown was a sinker. And although Archimedes' principle does apply to sinking objects too, which we'll get to, it's probably of greater interest for floating objects, so you can figure out things like how much cargo you can put in a ship, stuff like that. All right. So the idea here is that this is going to be some fluid, usually water, but doesn't matter, just some fluid. And let's say here's a fluid whose density does not change very rapidly with altitude, so we're imagining, say, air here. So at both of these locations, actually let me make these arrows a little less drastic. At both of these locations, we'll call this depth here depth 1. The pressure at depth 1 is equal to P atmosphere. And this is also atmospheric pressure up here. I mean, yes, technically there's a very slight difference due to the fact that the air has some density too. But air's density is, something like 1/700th-ish of water's. Air is 1.29 kilograms per cubic meter. Water is 1,000. So yeah, there you go. So we're not going to get ourselves too fussed about the slight difference in pressure from this surface here to that surface there. On the other hand, imagine, say, an ice cube or a block of wood or something like that floating in water. The bottom of it will be submerged down to some depth. We'll call that depth H. And we'll say that this is our depth number 2 right here that we're taking a look at. So down here at this surface, the pressure is P2. Okay. And just to be super careful here, because there are potentially 2 densities that we have to worry about, we will denote this density as rho sub F for the fluid. All right. So let's start by drawing a free body diagram for the block. Now here, we're going to have lateral forces due to pressure on each side. They're not terribly interesting. They're going to cancel. Again, this is because of Pascal's law here, saying the pressure has to be the same across all depths. So if it weren't, there'd be a pressure gradient our ice cube would move, and eventually we would settle out into some sort of equilibrium. But what we do have is we have a force of gravity acting on our ice cube. And we also have two other forces. We have a force due to the air above pushing down. So this will be equal to pressure at this depth. We'll say P1, same difference as P atmosphere. And then we also have to keep in mind that this surface right here has an area A, so that force will be equal to P1A. And that's also pushing down. I drew it greater here, but in reality it's probably less than gravity. In fact, let's just go with a reality here. Why not? Why don't we? There we go. F1. And then there's got to be a force pushing up on it. We'll call that F2. And that's due to the water underneath pushing up on it. So it'll be equal to P2 times that same surface area A. Okay. Now, this is one way you could draw the free body diagram. But what a lot of physicists do is they will define something called the buoyant force, B-O-U-Y-A-N-T. So just like buoy. So the buoyant force. And the buoyant force is just defined as F2 minus F1. So with that definition, I can replace this F2 and this F1 by drawing an equivalent free body diagram, which I'll draw in blue just to help keep it clear, where I have the buoyant force pointing up and gravity pointing down. And I still have my lateral forces here that cancel. So take your pick, but it's pretty standard to just draw in that buoyant force, and you quietly understand that it's that upward pointing F2 minus that downward pointing F1 to get the net force due to the pressure in the fluids. Okay, so we can figure out how much this buoyant force is. We can observe, so the buoyant force, like I said, is defined to be F2 minus F1. So this will be equal to P2A minus P1A. And we can use Pascal's principle here to say, all right, P2 is going to be equal to P1. Because keep in mind, we're fudging this a little bit. We're saying that both this surface and this surface are at pressure P1, which is basically true. P1 plus density of fluid, GH, A, minus P1A. So that cancels, and you are left with rho fluid, G, and then we got this AH. Well, let's sit and think carefully about what this AH means. Sorry, I forgot to label my H right there. So this AH would correspond to this volume right here. So it's the volume occupied by the object under the water line. We'll call it V sub D, and I'll get into what the D stands for in a second. I just want to be careful about that. So we can observe that this is this volume here. So we can write this as, finally, the density of the fluid times VD times G. Now we could take this a little further. This density of fluid times VD. This would correspond to a hypothetical mass of an amount of fluid equal to this volume. However, that volume of fluid need not actually exist, and I'll get into that. And even more annoyingly, what does that D in V sub D stand for, which is super duper standard notation for this? This gets called the displaced volume. And it's a great name, except for the fact that nothing is being displaced here. It's just the name for the volume under the water line. No fluid need ever have gotten pushed out of the way or anything like that. Where that idea comes from goes back to that idea that Archimedes had for figuring out the volume of King Solon's crown. There, Archimedes said, well, if I take a container that's big enough to hold a crown and I fill it up to the brim, then the spillage would have to match, the volume of the spillage would have to match the volume of the crown. So that's how Archimedes was able to figure out the volume of the crown, and then you can take the mass of the crown, divide by the volume, figure out the density of the crown, and see if that matched the density of the gold that was provided to the goldsmith. So in a situation like that, it's fair to say that, yes, some fluid got displaced out of the container, but let's say you're on an ocean. Where's it gonna go? You go stick a ship in the ocean, and where's the water? The water isn't spilling off the earth or anything like that. So for a lot of application, I think this name causes needless confusion. So I just prefer to say a phrase like the volume under the water line. That way we can recognize that it doesn't have to, that this amount of water need not have actually existed. In fact, to that point, I want you to think, the classic way of putting the question is, can you float a battleship in a bathtub? But maybe a better way to put the question is ask yourself, if I were to make like some sort of form-fitting swimming pool or something for a battleship, how much water would have to be in the pool in order to float the ship? So think about that for a second, pause the video, and then come back with me when you got an answer. All right, so I hope that you came to the conclusion that you need less than about a cup or so of water. And how do I come up with that? Well, let's imagine that you have the SS Gotham here. And now I'll have to be very careful lest the copyright strike people come after me. So let's say we've got our intrepid ship here, and some evil villain with the ability to freeze things on demand freezes the water outside of Gotham Harbor. And the intrepid SS Gotham is frozen into place. Now, I'm sure that some very some superhero with a deeply, deeply tortured psyche will eventually resolve the issue. But in the interim, let's say that you're the captain of the SS Gotham. Your first priority is to at least try to get the ship to float. And so you come up with an ingenious idea. You realize that the SS Gotham is completely frozen into Gotham Harbor. And so you get absolutely everybody in your crew to grab anything that remotely looks like a blowtorch, get down below the water line, and start blowing anything that looks like a blowtorch up against the metal hull, the inside of the metal hull of the SS Gotham. In so doing, you will eventually melt a very thin bead around the SS Gotham. So let me draw in blue here the liquid water that you now have around the SS Gotham. There you go. So that is the water that you're floating in. And you can tell just looking at it that the volume is an awful lot less than the volume of the SS Gotham. In fact, all you need is barely enough fluid to wet the hull, and then, yes, you are legitimately floating. So this layer could be just, a molecule or, just a few molecules thick, really. And a few molecules thick around the surface of a battleship. I don't know. Can't imagine being much more than a cup. So you don't need an awful lot of water to float a battleship if you've got the appropriate form-fitting swimming pool. And yes, it is legitimately floating. It's not touching up against any part here. And you know it's floating because why would the height change? You're frozen into place when the freeze ray was activated. You were at the height where you're floating to begin with. And now from the perspective of the ship, hey, I'm surrounded with water. There's absolutely no reason for the height of the ship to change. So yeah, you are floating on less than a cup of water. But the displaced volume of the ship is still this volume right here. So if you're going to go and plug into Archimedes' equation, that is still the V sub D that you plug in, because that is the volume below the water line. In this case, that volume is a heck of a lot bigger than the volume of the water you're actually floating in. That's why I said that this quote-unquote displaced volume, that that amount of fluid need never have existed. It's a horrible name, but I haven't seen anybody try to say anything else. And yes, before you get all fussed about the fact that I only did it here for a cube, and here now I did it for a whole shape, the result, even though I only did it for a cube, the result still applies. Alrighty, so even things that are sinking, though, also feel a buoyant force. And this is something that matters, especially to chemists when they're being very fussy. But let's just do a more straightforward example. Let's say you have yourself an iron cube. Now that's about the worst cube I've drawn in a long time. Let's try that again. There we go. So you have an iron cube. And let's say you want to weigh this cube. That all sounds good. Let's say the scale is calibrated in newtons, just so we're clear on that. But then, just for an added plot twist, let's say the entire contraption is stuck underwater. And you might say, well, gee, that sounds really dumb. And oh yeah, before you ask, the cube's 10 centimeters by 10 centimeters by 10 centimeters. So you might say, gee, that seems like a really dumb thing. Why would we care about that? Well, if you're designing a bridge, you might have some bridge supports underwater. But if you're a chemist, everything you measure is completely submerged in a fluid. And that fluid is air. And so if you're trying to measure out the mass of certain chemicals that have very low densities, this actually becomes something that you have to worry about and correct for. Because what does the scale read? The scale reads the normal force that's exerting on the cube. Now this normal force is going to turn out to be less than the force of gravity, because there's also a buoyant force pushing up on the cube from all the fluid. Again, in this example here, I'm just making an iron cube in water, but it could be just some chemical in air, whatever. So we can go ahead and figure out, what does the scale read here? Well, we can take our forces going up. That'll be the normal force plus the buoyant force. We subtract our forces going down. That's gravity. That has to equal ma sub y. But if we're reading on a scale, presumably the cube is at rest, so the acceleration is 0. So the normal force that you read on the scale, and this is true for any scale at all, reads less than the force of gravity on the thing unless you are in a vacuum chamber. So I take great comfort in this when I get out of the shower and I weigh myself, knowing that the reading says that's less than what I actually weigh. Okay, well, let's start to figure out what this would work out to be. So this would be the force of gravity is mg, and this here would, and this is going to be the density of the fluid times the displaced volume times g. Now here, let's go and identify our displaced volume. There it is. It's all of it. It's just equal to the volume of the cube. All right. So this is going to be, so the mass of the iron, we can say, is equal to the density of iron minus the times the volume of the thing. Now we got times g. We're subtracting the density of the fluid times that same volume, because in this case the entire object is under the water line, so the volume of the thing is the displaced volume. That's different from our battleship, where this is the volume of the battleship, but only that is the displaced volume. Or the ice cube, where this is the volume of the ice cube, but that is the displaced volume. Here, it's the whole thing. So we can pull out a V and a G from everything. So we have the density of iron minus the density of the fluid times Vg. Now, for a lot of solids and liquids, densities are on the order of hundreds or even thousands of kilograms per cubic meter. And air is 1.29 kilograms per cubic meter. So in a lot of practical applications, even chemical ones, you don't have to get too fussed about the difference. But there are certain things out there that are very fluffy. And if they're very fluffy, this difference in density is really going to matter. And so you have to correct for this to figure out what the actual mass of the chemical is. All right, if we go look in the tables, the density of iron is usually quoted as being something around 7,900 kilograms per cubic meter. Density of water is 1,000. Since I'm doing water here. The volume, well, it's a cube 0.1 meters on a side, so 0.1 meters cubed, then 9.8 newtons per kilogram. All right, well, I have meters cubed, meters that get cubed here, so they'll cancel the cubic meters there. Kilograms cancel kilograms there. That's all good. I'm left with newtons. And I get that instead of reading 79 newtons-ish, like you would think, a little under, you instead read 67.6 newtons. So, you know, it is a bit of a difference here. Now, if this were an air, you know, it's not moving things until like the third or fourth decimal place. So your third or fourth significant figure. So there, it's not such a big deal. But submerged in water, it matters. And these are things that you have to take into account, say, if you're designing a submarine or something like that. Okay, in the next video, we're going to start to get ourselves concerned with fluids moving, and we will go ahead and explore the equation of continuity. Catch you in the next one.